Welcome to another video lecture session on crystallography. So in this session, we are going to talk about coordination number in Bravais lattice and then find out the pecking fraction in a few crystal structures. So in the last section, we talked about Miller indices in different crystal structures. So continuing from that, we are now going to start with the first defining what is a coordination number. So in a given lattice, coordination number is the number of nearest neighbor atoms for different atoms present in the crystal. For example, see here I have drawn a simple cubic system, let's say. So in this case, it's a simple cubic system. So the lattice constant is A and it's same in all directions, right? And also I have not drawn just one unit cell, rather I have drawn 4 unit cell adjacent to each other. And if you concentrate on this corner position, so the atom which is there on this corner position would have 4 atoms sitting here, here, and here as nearest neighbor on this plane. And then it has another nearest neighbor which is here and which is at the next level up here, right? So how many such nearest neighbor atoms there? For the simple cubic system, 4 on the same level, 1 at the bottom surface and 1 at the top surface. So in total 6. So that means for the simple cubic system, 6 is the coordination number, right? So similarly, if you have a body-centered system, BCC system, where you have a cubic unit cell like here as it is described, you have a body-centered atom and then 8 different atoms sitting at the corners. So for this atom, how many nearest neighbors are there? 8 different nearest neighbors, right? So for the BCC, the coordination number is 8. It doesn't matter. Even if you start with the corner atoms, you will again find that there are 8 nearest neighbors. So what are those 8 nearest neighbors? Like you start with, let's say now we are considering the body-centered atoms. Body-centered Bravais lattice. So that means these atoms are there, but then there is another atom at the center of each of these unit cells, right? So that means if I take this corner atom, then who is the closest one? These corner atoms are not now, in case of body-centered Bravais lattice, corner atoms are not the nearest neighbors. The nearest neighbor atoms are, for each of these corner atoms, the body-centered atoms are the nearest neighbors. So for this body-centered atom, 4 different body-centered atoms on this layer as the body-centered atoms of these 4 different cubes on the same layer. And then there would be another layer here, right? Above this corner atoms. So again 4 more body-centered atoms right at the top of each of these body-centered atoms, right? So for this corner atom, 4 body-centered atom on the lower level and 4 at the top level. And that's how for the body-centered atom, 8 nearest neighbors are there. So coordination number is 8 as it is written here, right? So in case of face-centered system, so these are the face-centered coordinate atoms in a FCC Bravais lattice. You can see here that for this face-centered atom, 1, 2, 3, 4 atoms are here on this level, on this face, nearest neighbors. Then, so for this atom, 1, 2, 3, 4 atoms, then it is also having. So if I take a large version of this, what we have here is that for this particular atom, 4 nearest neighbors are these. Then these are also its nearest neighbors, these 2. And similarly, if you draw another unit cell here, what you would see is that 1 more atom on this face, 1 more atom on the back face, 1 more on the top face, and 1 more in the front face. So this face centered atom is on this front face. So for this atom, this, which is on the same level, are also its nearest neighbors. So how many up to now? 1, 2, 3, 4, then 4 more, 5, 6, 7, 8, and again these are also its nearest neighbors. These atoms would also touch this face centered atoms. So already we have 8, and then these atoms 1, 2, 3, 4. So in total we have 12 nearest neighbor for the face centered atoms. So that means for the face centered Bravais lattice, we have coordination number is equal to 12. For the hexagonal closed pack system, it's comparatively easier to think. So this is our hexagonal closed pack system. So the unit cell would be something like this. So this is our unit cell. So this from here to here to here to here, and then from here, here. So this is our unit cell, and there is, so in this hexagonal closed pack system, again the coordination number is 12. So that means for each of these atoms you will find 12 nearest neighbors. Like for this atom, the easiest one to look at is this atom. So this atom, how many nearest neighbors are there on the same level? 6 different nearest neighbors. 1, 2, 3, 4, 5, 6. So these atoms are its nearest neighbor. Then 3 more on the lower surface. So 1, 2, 3. So this atom actually would touch these 3 atoms. So 3 more here, and again you will find 3 more here. Just like these, identical 3 more in their position, but on this upper layer, right? So 3 on the upper layer, 3 on the lower layer, and on the same layer 6. So in total 12 coordination number, and this is clear also from this figure. So this is the atom, that this atom is here. So 3 atoms, these 3 atoms, and then these 6 atoms, and then there would be 3 more atoms here. So 6 here, 3 here. So altogether you have 12 atoms in the hexagonal closed pack systems. So 12 nearest neighbors. So coordination number is equal to 12. Next we have to define something called atomic packing factor. What is atomic packing factor? This atomic packing factor actually determines how closely, it's a number, it's a ratio of volumes, and this ratio is a unitless number, and this defines how much closely the atoms are packed within a given Bravais lattice. So if I find this atomic packing factor is like 1, then that means within that cell, Bravais lattice unit cell, each and every part of that cell, of each and every corner of that volume of that cell is occupied by atoms, not any empty space. But of course, atoms are circular in shape, unit cells are not. For example, mostly they are some, cubic form, distorted maybe. So these two configurations should never fit perfectly, and that's why if you could find some unit cell to be spherical in nature, then probably you will find atomic packing factor to be equal to 1, but you don't. So you have always some space left out, they are not filled. So you will never find a system where atomic packing fraction is exactly equal to 1. So how to define that? That definition is volume of the atoms. So for example, in case of hexagonal closed pack system, first you will find, given a unit cell, how many atoms are there, and for each atom you find, let's say there are in a given Bravais lattice, there are only one atom per unit cell, then the volume of that atom would come on the top, and then volume of the unit cell, then the whole unit cell volume is at the bottom. And you take this ratio, and that ratio would be called your atomic packing fraction. Let's try to find out this packing fraction for simple cubic, FCC, BCC, and HCP, hexagonal closed pack systems. So for doing this, for FCC system, first you have to find out how many such atoms are there in a given unit cell, right? So in a FCC system, okay, before we go to FCC system, we can find out how many such atoms are there in a simple cubic system. So like already we have, so this is our, let's say, a cubic system, simple cubic. So this is our cube and this is our unit cell. So at each different corners we have one atom, right? So remember, actually these atoms would touch each other. I'm not drawing the big atom, so in that case, if I do, then these background atoms will be, obscured. But do remember, when I draw these atoms, they are actually this big, that nearest neighbors would always touch each other, like we have shown here they would touch each other. Okay, so here 4 on each level in that unit cell. So that means this atom here is touched by this atom, and also one more here, right? So this atom is shared by 4 unit cell on this layer, and 4 unit cell on this layer. So that's how you have that total number of unit cells that this corner is shared with is equal to 8. 4 on this layer, 4 on this layer. So that means this corner atom is only contributing to this our unit cell 1/8. So one atom is contributing 1/8. Then there are 8 different atoms. So in total, in a simple cubic system, how many atoms are there? Total numbers of atom 1. Effectively 1 atom is there, because each corner contributes 1/8, right? 1 atom. How? Each corner contributes 8, and there are 8 different corners where atoms are there. So 8 into 8 is equal to 1. So 8 effectively atoms are there in a simple cubic system. In case of a face-centered system, face-centered simple cubic, you will have again 8 corners. So 1, and this is due to corner atoms, plus there are some face atoms, right? So let's say this atom which is there on this face, then this atom is shared with 2 unit cell. One is this adjacent unit cell here, right? So that means this atom is contributing only half to this unit cell, our original unit cell, and half with this nearest unit cell here. So that means this atom is sharing half of its whole. So how many such face atoms are there? 6 different faces, so 6 different units, face atoms. So that means in total 3 atoms here, and these are face atoms. Effectively 3 face atoms and 1 corner atom. Altogether 4 atoms are there in a face-centered cubic system. What would be the BCC system? In BCC system, you have your unit cell, which is cubic, and there is one atom at the center. And 4 on this layer, 4 on this layer. So again, for BCC, you have one corner atom plus one at the center. So one center. So in total you have 2 atoms in case of BCC systems. So that you need, because then you can find out what is the atomic volume of the atoms in the atomic packing factor calculations, right? So remember that. So let's find out for the FCC. So if each of these atoms has a radius is equal to r, then in case of FCC, you have 4 into 4 by 3 pi r cube. The radius of each of these atoms is r. So total volume for the atoms is 4 into 4 by 3 pi r cube. And if you look at this face-centered cube, where A is the length of the unit cell, so this much is A, then from here you can calculate using Pythagoras theorem that this length is equal to square root 2A, this one. And in terms of radius of the atoms, this is r, this is the diameter of this atom, so 2r here. So in total 4r, so you have square root 2a is equal to 4r. So from here you can find some relationship between a and capital R, which is the radius of the atom. And then you take the ratio is this volume of the atoms and the volume of the unit cell. The volume of the unit cell is, if A is the lattice constant, that means side length, then it's a cube, it's a cube. So a cube 4 into, this is the total volume of the atoms that are there in this. So you see this empty space are there within the unit cell. So due to these empty spaces, you would have that the atomic packing factor is not equal to 1, it's less than that. And when you put replace this R with the A from this relationship, you would take the ratio and calculate it. It would turn out to be equal to 0.74. That means atomic packing factor for FCC lattice is 0.74. And then you calculate it for the BCC system. So in case of BCC system, everything is more or less same, means the procedurally. So how many atoms are there? We have already calculated for BCC system, 2 atoms are there per unit cell. So the total atomic volume is 2 into 4 by 3 pi r cube, if r is the radius of the atoms. How much is the volume of that unit cell? Again, a cube, it's a cubic system. And then you have to find out what's the relationship between this r and a. How to find that out? You take this diagonal of this unit cell, because the atom is at the center. So this corner atom touches the center atom, then this corner atom touches the center atom. So in together, this length is square root 3 into a, and that is equal to 1r, 2r, and this 2r. So in together, there are 4r. So square root 3 is equal to 4r. And from here, you can replace this r here and find out that the APF or atomic packing factor is equal to 0.68. So that means in BCC system, the atoms are slightly less closely packed compared to FCC. So in FCC it's 0.74 and BCC it's 0.68. So that's slightly less. Let's see what it is in case of hexagonal lattice, hexagonal closed pack system. So this is a hexagonal closed pack system, right? So this is the hexagon here, and there is this one atom at the center. So in this case, this is a, so first let us find out if this is equal to A, that's the lattice constant of this hexagonal system, then how much is A? So if the radius of this atom is R and this atom is R, so A is equal to 2R, and which is here, A is equal to 2R. So what is the volume, atomic volume in this system for the HCP? Atomic volume would be 6. 6 is the number of atom multiplied by 4 by 3 pi R cube. And then using this relationship, you can replace R with A. And that will come on the top of this atomic packing factor. And then we have to find out the volume of the unit cell. What is the volume of the unit cell? So if you like, first let's look at this bottom surface. So that's a hexagon, or the top one, it doesn't matter. So that's a hexagon, and this hexagon is here, right? So in this hexagon, what is the area of this one of this triangle? So that's my unit lattice constant, which is equal to A. And then we have to find out area half into A into H. H is the height, this height. So that's the H here, right? So from here, if you look closely, this is a isosceles triangle. All sides are equal. So this is 60, this is 60, and from here you can say H is equal to A into sine 60. And then the volume, so that's the area of one of the triangle. So there are 6 triangles. So 6 into half into A into H. And to find out the volume of this whole cell, you have to multiply it by its height. And this height is C. So that's the volume of this unit cell. So that's the volume. And when you put it there, so you have 3A square C into sine 60. And you have it here. So that's the volume. And this is that's the volume of the atom. This is the volume of this cell. And from this triangle, actually you can calculate what is the relationship between this length A and this C. Okay. And from there, if you replace, it's described here. So C by A ratio is equal to actually 1.633. That's a separate calculation, and that's only a simple geometry. I'm not going into that. Assuming that you would be able to find out C by A ratio is equal to 1.633 given such a configuration, you would see that atomic packing factor is 0.74, which is again same as, that's what you see in case of FCC too. So that means HCP and FCC, in terms of their volume occupied or how closely packed they are same. They are same in terms of their packedness. And with this, we end this lecture session, and also we conclude the part of the crystallography. Thank you very much. So again, let us repeat. In this crystallography, in 3 different lecture sessions, we have discussed different crystal structures defined by their Bravais lattice. We tried to understand what are called Miller indices, then directions and planes in case of crystal structures, the interplanar spacing, then we looked at coordination number, the packing fraction, atomic packing fraction. So, thank you.